My name is Tomczak. I'm now at King's College London most of the time, and some of the time still in Vienna at the TU. And I will be talking about quasi 2D systems and their simulation. And yeah, 20 years ago, basically, this whole field opened up a new direction with the advent of the exfoliation techniques that really allowed the synthesization of really freestanding 2D systems like graphene, and transition metal decalcogenides. But at the same time, actually, there was other 2D physics that came into being, more in the world that I'm more interested in that of oxides, and namely the emergence of a 2D electron gas at the interface of two different oxides. And at the heart of this was the advance in experimental synthesization techniques that allowed for even yet another route to obtain 2D systems, and that is atomical precise deposition of individual layers on substrates with which you can deposit oxides and other systems on a substrate layer by layer, and you can really control. You have 1 layer, 2 layer, 3 layer, you get atomic control, and that is one way to go towards another route towards going to quasi 2D systems on an insulating substrate. And when I say 2D systems, I mean there are many people are working now on bilayer graphene and twisted bilayer graphene, which is very en vogue. Here I will talk more about the more classical kind of systems, which for me is oxides, where most of my research comes from on substrates. And so I will talk about the 2D route of dimensional reduction of oxides as thin films. However, as also one part, I will talk about things that are geared towards transition metal decalcogenides. So this is the outline of my talk. I will basically talk about 3 things. The first two concern these oxide films, and the first part would be structurally. So what is, if you come from a material that exists in the bulk and you deposit it as a monolayer or a finite layer on the substrate, what are the things that we need to take into account? What changes with respect to the bulk? The second part will deal with what we've just heard from Ryotaro. If one is in 2 dimensions, DMFT might not be the method of choice in all the regions of phase space. So we want to take into account non-local renormalizations. This will be a rather brief part. And in a third part, I will talk about going beyond the Hubbard model. So here, basically in the point 1 and 2, we're always solving with one technique or the other a multi-orbital Hubbard model, and we're just changing the technique that we're upgrading. But here I'll say that we might have to change the Hamiltonian that we're looking at. In particular, this has to do with long-range interactions. All right, the first part, this is work done by my PhD student in Vienna, Matthias Pickham, who will graduate soon, so he should get the credit for all what I'm talking about. Okay, so let's get started. So what happens if you have a material that you deposit on as a finite film onto a substrate? And here I will mainly talk about three effects that take place. One is if you put a thin film in Z direction, let's say you deposit it in Z direction, the system is finite, so you lose translational invariance. So you have something like a potential well that has this width here. And as you all know from quantum mechanics, then you will have quantum well states, and you see this kind of offset in the dispersion here in the Z direction. And this is sure what you see so this is one example for a relatively boring bulk oxide, strontium vanadate, which has 1 electron, and these are the T2G orbitals, the low energy degrees of freedom. If you deposit this on STO, for example, here, you see the band structure becomes more complicated, and sure enough, you see here these quantum well states, this stacking up of excitations. And the important thing to see here is that it's not all of the orbitals or all of the bands that develop these quantum wells. Of course, there is a connection between the deposition direction and the direction of the orbitals that are dominating the characters of these bands. So you have orbital physics coming into play, whereas the in-plane orbital will be relatively unaffected, these quantum world states emerge for the XZ and YZ that have an orientation in the Z direction. And on top of that, you have a reduction of kinetic energy because, of course, you cannot hop into the vacuum. Okay. Then there is strain. So if you deposit a material onto another material, sure enough, the lattice constant will be different. And that has been summarized very nicely in this recent paper here. So basically, you compress or strain your system. And taking again the example of strontium vanadate, which is perfectly cubic, which has here the vanadium in the middle, and you have this coordination polyhedra. You shrink or expand it, and with that you're going to lose the degeneracy of these T2G orbitals that I was talking about. Again, orbital physics. So when you do it this way, you expand it in the XY plane, then this XY orbital goes down and the other ones go up. So again, you have a structural effect that affects orbitals differently because there's a directional thing to it. So crystal fields will change, but also kinetic energy. If you compress something, there will be more delocalization and more kinetic energy. And let me briefly say that this is not just a nuisance to calculate, but this can actually be used as a tuning knob. So you can have one system that has one physical effect. You put it on different substrates and you monitor what happens to this system. And this is one example here I'm showing here on the left. So this is a cuprid deposited on a substrate. And by varying the substrate, you can identify that substrate, which maximizes the super exchange, will, under doping, develop the largest superconducting temperature. So you can sort of optimize by choosing your substrate strain another property, though, and see maybe at least some empirical link between the strain and the high temperature, superconducting temperature. And the third effect is termination. So we talked about something on the substrate, but there's also the vacuum on the other side. And of course, it depends very much, as we will see, the physics on what does the system terminate with. So here, this seems to be quite intuitive that you put one unit cell of this oxide that you grow on the substrate. Here you would have something where, a VO2 termination you're missing. You're only putting half of a unit cell there. This looks less intuitive, but in fact, experimentally, they tell us that this is what is realized. So if you grow one monolayer of this oxide on STO, it's not an entire unit cell that goes there, but only half of it, and that will have consequences. And on top of that, well, there's oxygen around. There can always be oxygen vacancies, which I will not talk about, but you can have the opposite. You can have surplus oxygen that goes into this apical position here, and that decorates some or all of the vanadium atoms. And indeed, that is what happens for thick films. So this is an experimental work where we did some simulations. This is when you deposit a large or a thick film on a substrate. You indeed have that every second of these vanadium atoms gets an apical oxygen, and that sucks out the one electron that each vanadium has, and basically creates a neutral or a dead layer here on top. So basically, if we do it like this, so here you are, not does this work? Here you're basically sucking the electrons out of the vanadium, and then the top layer becomes insulating, as you see here, and that's as if this layer here does not exist. And so the quantum world state that I was talking about, well, there should be less now with this apical oxygen because there is one layer less that is electronically active. And if you believe experimentalists, how they extract dispersions from their photo emission intensity, that is what you see here in the experiment. So at least qualitatively. Okay, but now, so we had thick films, thin films. What happens as a function of the thickness? So if we have a thick film, which is basically bulk-like, then the system that I'm talking about is relatively boring. It's a correlated metal with an effective mass of 2 from specific heat or from photoemission spectroscopy. But if you go down in number of layers, so here you go to thinner and thinner films, at the very bottom, you see that there's the opening of a gap in these photoemission spectra. So you have a transition from a correlated metal to an insulator state. And that we simulated already a while ago in the group of Carsten Held, and this is from Zicheng Zhong, already in 2015. This is the two layers on top of STO. And sure enough, if we do DMFT for it, we see that it is insulating. So there's a gap in the top layer of this system and also in the interface layer, the bottom layer here, the spectral function is gapped. And sure enough, what I was talking about, or what I tried to emphasize before, is that orbital physics is important, because it's not that you just have a reduction of kinetic energy and the system becomes not insulating because of that, but you have an orbital polarization in the system. And so this one electron that's on the vanadium is hosted by only a single orbital, which then has a lower critical U and becomes insulated. So in fact, this is relatively similar to the story of Silke and Eva in yttrium titanate, where you also have a symmetry breaking and you have one effective orbital that turns then insulating when you turn on correlations. Now, the interesting thing here is that this has a relatively small gap. If you look for the U, I think here was 3.5 or so. The gap in relation is relatively small, so it's relatively stable, so you can easily manipulate it. And the interesting thing is that if you apply a gate voltage, you can, or basically you dope the system, you can drive the system from an insulator. This is the spectral function at the Fermi level with a relatively small gate voltage into a metallic state. And that could be used into in a sort of oxide electronic realm that you can make a transistor out of this. So you could construct, although it's experimentally difficult, a mod transistor from this system. Okay. Now, so this was a while ago, and what we asked ourselves now is, besides metal insulator transition as a function of doping, so a filling controlled mod transition, does something else happen? Are there ordered phases or other fluctuations? So basically, we're asking, if we dope the system, what is the phase diagram of this ultra thin film? And to make things easy, we use really the monolayer. We just use one, with the wrong termination, one unit cell of strontium vanadate on top of this STO film, compute still within dynamical mean field theory the physical susceptibilities and look for instabilities there. And we're doing that for both terminations, so the wrong one and the one that is actually observed. And when we do that, we get two very rich and very different phase diagrams. So here we have, okay, they're both mod insulating at nominal filling. But then if we go away here, this one has an antiferromagnetic regime. At larger doping becomes ferromagnetic. Then there's some checkerboard orbital ordering here at large doping, which dominates already the nominal region in the other termination here. And then there's some stripe orbital ordering and some incommensurate phase. So it's a very, just having or having not this extra oxygen and strontium here changes the picture completely. And we have turned something that is relatively boring, strontium vanadate, into something that has a very complex phase diagram. And here I just want to motivate for those dominating phases here, what is the sort of the intuitive physical understanding? Why do we have these phases? And that has, of course, to do, that's why I did this whole introduction, to do with the orbitals and with the structural effects that I was talking about. So here we have the rather canonical case in this unit cell that the substrate strain and the confinement conspire in having the degeneracy lifted and this XY orbital going down. So we have one electron in one orbital on a bipartite, yeah, not bipartite, that's the other case, on a square kind of lattice. And so just like in cuprates, the system can gain kinetic energy by doing the virtual hopping, the sort of super exchange. Just like in cuprates, you have the sort of an instability towards antiferromagnetic order. Here on the other side, of course, something different must happen. And in fact, what happens is just the opposite. So this severing of this octahedron here, cutting it into half, turns the thing upside down. Now you have the two orbitals that are along the z direction to be energetically favorable. You have one electron there. So you have quarter filling, two orbitals quarter filled, and that is known from classical works that this obviously on the bipartite lattice that this favors a charge order in the checkerboard configuration. And this is one case where, although there's just one electron, the Hund's rule coupling is actually important. Okay, so in this case, I just wanted to motivate that there is rich physics can come about from relatively boring materials, because you have an extra, well, boring means basically that they're somewhat isotropic or cubic, and you can create richness and introduce new energy scales by perturbing the system. And one way of doing it is to go to the two-dimensional limit when geometric constraints cause the breaking of symmetries, and the whole system becomes more fragile, and you can go through phase space and realize all sorts of different phases. Okay, that would be part one. Now part two is to go beyond DMFT. So we know DMFT is a spatial mean field, and so in 2 dimensions it's not always adequate to use it. And as we have heard in the talk before, there's cluster extensions and there's diagrammatic extensions. And here we're going to use the one, the last one that Ryotaro used in his talk, and the one that has been introduced, I presume, by Carsten Held in the November edition that I still have to watch on YouTube, the dynamical vertex approximation, where the equation of motion for the interesting part of the self-energy looks like this. Okay, so let's do this for this system, and I'm choosing here one region in phase space where we are closer to the vicinity of an antiferromagnetic instability at some electron doping here, and this is what we get for the XY orbital Fermi surface sheet. And I can tell you that's not so visible, that the change in intensity here has to do with orbital character, whereas the scattering rate on this Fermi surface is constant, so there's no real momentum selectivity on the Fermi surface here. However, and that connects a little bit to what Ryotaro had, or what you had the plot as im sigma as a function along a path. Here you have a relatively benign self-energy at the gamma point in the middle for the occupied part here, still large, but sort of Fermi liquid-like. And outside of the Fermi surface, you have very strong renormalization for momenta that are outside of the Fermi surface. So it makes really a large difference whether you're here in the blue or here in the blue. And I'm not going too much into the details, but what we have wondered ourselves, or let's say this observation has prompted us to analyze this equation of motion a bit more detailed, and we have like an addition to something that Thomas was talking about last year. We have an addition to the sort of diagnostics tools of non-local renormalizations. So we can write this equation into the sum over. So basically, we do just a relabeling of momenta, and we can rewrite the self-energy as a quantity that depends on the outside momentum k, and it is averaged over the Brillouin zone over a momentum k double prime. And why is this useful? Because this quantity we can write like this, and it separates sort of the spectral ingredient at k double prime, this Green's function, to the fluctuations that happen unless we have that happen here. And let's say we don't have nesting, then this chi0 is benign. And all of the fluctuations will arise if we are in the vicinity of an instability from the full vertex F at the characteristic momentum vector k prime minus k, which in our case will be, because we're close to the antiferromagnetic dome, at q equals pi pi. And now we can look, how does this function look like for these k points resolved into k double prime? Okay, we're going to lowest Matsubara frequencies. And so what we see is that if we have a momentum k, so this is the outside momentum k that is here, if the vector, the characteristic vector associated with the dominant fluctuations, in this case pi, connects to the DMFT Fermi surface, then this quantity is large. Yeah, so this explains why we have a large renormalization for this blue K1 outside here, because we can connect it with the fluctuation vector to the Fermi surface. The same thing is possible for K2, but it's not possible for K3. The one in the middle here, I cannot connect with the pi to the Fermi surface. It's always outside. And that also explains why we don't see a momentum differentiation on the Fermi surface, because let me see whether this works. If I'm sitting on the Fermi surface here, if I'm having here the QQ vector, then I'm always outside. So basically the Fermi surface is too small to generate any sizable non-local signatures in the renormalization on the Fermi surface, because the target, the direction, the K prime needs to be on the Fermi surface as well. And okay, so this kind of combines aspects of fluctuation diagnostics that Thomas was talking about, and also the spectral ingredient that Friedrich Krien has a recent paper on. And okay, since it's kind of both a little bit, we had like a fancy name, and we call this binaural for like stereo fluctuation diagnostics. Okay. All right, with that, I'm coming already to the last part of my talk, and that is going beyond the Hubbard model. So changing basically the Hamiltonian. Before, in 1 and 2, we always looked at the glorified multi-orbital Hubbard model with some realistic hoppings, etc., but always local interaction. And here we're going to need something better. And this work is really driven by Eric von Loon. And it's been long in the making, so it's from 2023, but we started this a long time ago, and this might have been because every author, except Giorgio, every author on the list has changed institution during working on this project, and I guess that has slowed down things a little bit. Although Giorgio, I hear, has gotten a local promotion, so I guess that also kind of counts. Okay. So the principle or the rationale of this work is relatively easy. So we have a two-dimensional system. We say it's a Mott insulator when it's freestanding. So it's insulating. And now if we put or bring a dielectric into the vicinity of this monolayer or this 2D system, then how the Coulomb interaction is screened will change depending on what's the dielectric property of this environment or the probe that we bring close to it. And so the question is, can we, if we start out from a Mott insulator when it's in vacuum, reduce the Coulomb interaction enough with realistic dielectrica to induce an insulator to metal transition in the system? And so the way we or Eric models is we use an extended Hubbard model here. So on the triangular lattice, because our motivation are transition metal dechalcogenide structures with the long-range Coulomb interaction. And indeed, the reason we need this long-range Coulomb interaction is that screening is not just dynamic, but also has to do with the range. So and screening, in particular in 2D systems, is imperfect. So there is a lot of remnant of the unscreened 1/r Coulomb interaction, and so this is important here. And we're not going to do this really microscopically or atomistic. We're going to use electrostatic. So this is a proof of principle calculation. We're using an electrostatic ansatz to compute the Coulomb interaction. That only depends on 2 parameters, several parameters. Some is the geometry of the system, so the height of the monolayer, the lattice constant, and the dielectric constants of the environment and the Mott layer itself. This is the formula that you get. So this is nothing new. This was already used in these papers here. The first part is the partially screened Coulomb interaction in 2D. So this epsilon m basically takes into account the screening of all higher energy degrees of freedom, so everything that's not near the Fermi level. And only this second factor here models the embedding, the environment, and that depends on the geometry, here on the height of the monolayer, and okay, also on the lattice constant via Q, and on the difference or ratio of the dielectric constants between the environment and the layer itself. And as you see, this for Q going to infinity, this one goes to 1. So really the dominant thing, short range, if we want to see a difference through this factor in the simulations, then we cannot limit ourselves to a local interaction. We really need a longer range interaction. And what we and Eric used here is the dual boson approach. Now, does this work? Yes, it does, because what you've seen here is already actual data. So this is a simulated spectral function of this model. And if we look at this momentum resolved, so this is for different environment screenings. This is the vacuum. You see the original band structure is this line here. If you turn on correlations in the dual boson approach, you get this lower and upper Hubbard band. So it's an insulator. This corresponds to the freestanding layer in vacuum. And then if you increase the environmental screening with this dielectric constant here, reaching values that are somewhat realistic and compared to silicon oxide, you see a weakening. And here at epsilon equal 5, already you see some metallicity here at the Fermi level if you take the local the momentum average. And then at epsilon equals 10, which is still lower than what you have for silicon, you clearly have a quasi-particle peak and a metallic system. Now, so this was one ingredient here, was changing the environment. If we look again at this formula, this correction factor, this additional screening on top of epsilon m is large if the environment has a large dielectric constant. So for the layer we used 5 and scanned here through, and so for let's say 5 and 10 is already enough to make this significant. The second ingredient is the geometry of the mod layer itself. So here in the exponential you have Q times H, which is proportional to H over A, meaning the height of the layer divided by the lattice constant. That needs to be small for this screening here to be effective or significant. Here we used A equals H, so something like a height equals the sort of kind of a squarish regime. But realistically, for some of these materials, we don't reach that. So for transition metal dechalcogenates, one gets something that's lower than 2. Cuprates, which I was astonished to hear, can also be exfoliated these days. Well, one gets H over A is 4, which is relatively large. So the question is this in any way realistic? Can this be realized in experiment where we could see this transition? Well, this can be helped by one thing, and that is superstructure. So you can artificially increase your lattice constant. So, you know, in bilayer graphene, the lattice constant is enormous. Of course, the physics is more complicated than a simple knot insulator. Or in this system that I mentioned in the beginning, this thallium D sulfide, that has a charge density wave reconstruction that also shown here largely increases the lattice spacing. So we are hopeful that there is a system that in realistic regions of the dielectric screening from the environment can be tuned from, to generate this metal, this insulator to metal transition. Now, why is this of any interest? And that kind of makes the connection with what I was talking about in the beginning, the other system. So we have a Mott insulator in 2 dimensions. We can metallize it by sticking a dielectric on top of it. Now here I've done this globally, but what one could imagine doing, of course, this is a bit of a hypothesis, is that one does this spatially resolved. Yeah, I can have a Mott insulator layer, and then by lithography or etching, one could create a spatially resolved dielectric occupation in some regions and others not, and thereby kind of creating metallic regions which I could build circuitry from. So this combines very well with the previous project. So here one could create metallic circuitry on a Mott insulator, and for the other regions one could, so this is by dielectric Coulomb engineering, and here I have the control by additionally switching maybe this insulator in the middle to become metallic if I additionally apply a field. So this kind of uses as a host a Mott insulator, and I manipulate it by dielectric Coulomb engineering to have circuitry, and by additionally applying a field, I could add some switching capabilities to that. Of course, that's a bit a theorist talking, because of course one needs to gate all these systems, and it's complicated, but at least in our theoretist toolbox, one can play with that. Okay, and with that, I'm already at the end of my talk. I hope I convinced you that also boring materials can be made interesting if you add geometric constraints that kind of activate orbital degrees of freedom in the system, and that these then are very sensitive to small changes, and we get, just like for other correlated materials, a very rich phase diagrams that can be explored by, for in this case, doping or gate voltage. I've given you a small addition to the diagnostic toolbox that connects non-local fluctuations to non-local correlations. And in the third case, I advocated that by manipulating the environment of a 2D material, we could possibly create some kind of devices in which a Mott insulator can be or circuitry can be built by adding spatially localized dielectric on the Mott insulator. Okay, and with that, I thank you, and that would be it. Thank you.
Great. Let's thank Jan again for the great talk. We are now open for questions. Please raise your hand. First, we have nobody yet. Antoine has a question.
Just a quick question. So you very nicely demonstrated the fact that when you grow, for example, a very thin layer of strontium VO3, it becomes an insulator. And you emphasized different effects that can be responsible for that. In that specific case, what was the main effect? Was it the lifting of degeneracy, orbital degeneracy, and at the same time the reduction of the bandwidth? Or
yes, so you can as a theoretist, of course, play and say you hold one thing fixed and change the other one. So in this case, when you go down with the layers, the important thing is the degeneracy lifting. So it's the crystal field / confinement. It's the lifting of the degeneracy that is important for the transition at like 2 or 3 layers that turns insulating.
Okay, thank you.
Any other question?
No more questions?
So either it was clear or boring.
Oh, it was a very nice talk.
Jan, maybe I would have a question.
Oh, hi,
hi, how are you? So I'm curious about this last part. So here you dominantly screen the local or longer range interaction, because the two might actually have opposite effects. If you screen Hubbard repulsion, it makes the thing more metallic, but longer range repulsion will have opposite effect, right? Screening of the long range.
That's correct. Yeah. So in this kind of ansatz here, indeed, this effect, sort of this additional screening is largest for small q. So that means a rather longer range interactions. That's true. So you would think, in principle, if you would limit yourself just to local and nearest neighbor, that the non-local one would indeed favor the more screening would favor the insulator because typically the non-local part gets screened more effectively than the local part. But here it turns out that the overall balance is that the effect on the local one. I mean, I guess we could plot this via V of Q or the Fourier transform. Actually reduces both the on-site and slightly and the non-local one. So basically both get reduced, but the non-local one gets reduced faster. But overall, the effect is there that the correlation strength becomes weaker.
Okay, interesting.
But of course, it's an electrostatic modeling. So if one has something that is more sort of with more localized wave functions and more atomistic, so this definitely calls for a more realistic CRPA calculation, for example, for bringing things into the environment. But in this electrostatic model, it does work.
Let me add another question on the same subject. So, I mean, if you, let's say, when you look at this tantalum disulfide, right, this monolayer there has like very narrow bandwidth. So, I mean, here you had in mind that you just make this electrostatic screening by a substrate, or it's just proximity. This was because if you put a substrate, this will also affect these tiny hopping matrix elements.
Yes. Okay, so here we had a hopping of 0.3, which is maybe too large compared for this system. And what I shown in the modeling here was that with respect to the freestanding, so that you put the dielectric environment from both sides directly on the monolayer. But we have, I think it's in the appendix also, where we look at one-sided screening. So if you have this thing on top of the substrate, then of course you have only control over what happens on. I mean, first, then the substrate modifies the monolayer, and you only have control over one side. You can only tune the thing or change the screening from one side by putting a dielectric on. So then the effect will become weaker as well.
Okay, thank you.